All right, talking about the Koppers Aromatic prop, and a statement that I was going to make before I decided to be hungry.
Hey, Kevin, I don't think any of us can see your notepad.
Everybody can see it but you.
Um,
Yeah,
I'm
I see
trying
it.
to.
Yeah?
I can't.
Oh,
Try to
there we go.
refresh your browser. How about now?
Yep, there we go. Thank you.
Okay. Due to advances. All right, so due to advances in constant speed props. The aromatics are no longer, or they're pretty rare. I don't think I've ever worked on a plane with one. Aromatic props are pretty rare, but still used. Pretty rare, but still used. All right, so here's what I'm going to do. I'm going to go through my notes and the slides, and I'll explain to you how it works. If you get it, awesome. If you don't, that's okay. Because I'm not going to write it. So if you know if I'm not writing it, I'm not asking it on the test. So, all right. Oops, I need to bring up my slides so I can know which slide I want next. Okay. It's actually kind of difficult here, but I'll go with it. So operation of flight. The stability of the aromatic propeller is obtained by balancing the pitch decreasing effect of the aromatic forces with the pitch increasing effect of the net centrifugal force acting on the masses of blade and counterweights. Let me try that one more time for you. So the stability of the prop, stability because it rotates back and forth, high pitch, low pitch, and it moves super easy. If you could touch one and move it, there's zero resistance between the pitch change mechanism. It's on dry bearings or oil bearings. There's no resistance. So the stability of the prop is obtained by balancing the pitch decreasing effect of the aerodynamic force. So aerodynamic forces are, pitch decreasing with the pitch increasing effect of the centrifugal force acting on the blade and counterweight. And I'm going to tell you this, you always look at any kind of propeller, and you're going to get into this here with me in just a little bit. You always look for it. And anytime you have counterweights are used in an opposite fashion. Let me back up one step. So we know that, I'll go this way and then come back. We know that centrifugal twisting force is one of the greatest effects, not but let's say the second greatest effect on the prop. And centrifugal twisting force will always bring a blade to low angle, right? A low blade angle. And if you add counterweights, it does the opposite. The counterweights are always put in such an area that they override the centrifugal twisting force of a blade, and the counterweights are mounted kind of out here, and then they want to go this way and bring the blade to a feather position. So that's how you change the momentum. And we're going to see that we do this with constant speed props. Some constant speed props are designed so that centrifugal twisting force makes them go to a low blade angle, and some are designed to go to a high blade angle. How do you change it from that? You add counterweights. So all you do is look at a prop with counterweights, and now I know that centrifugal force is going to make it go towards a high blade angle, the opposite of without. So, and I'm going to write that as we go with some other props, but for this one, I'm just going to kind of go through it. So according to this one, the pitch decreasing effect is aerodynamic, and the pitch increasing is the counterweights. All right. And so you just have to balance those two things out. So at takeoff, the pitch decreasing forces are greatest, pitch decreasing, which is aromatic. And therefore the blade will move forward. See, now it moves forward and aft, which is really the key to this thing. And it's so hard to show you how it does that. I think the best pitch is this picture sort of describes it the best, how it's in this weird eccentric movement. And that's all part of why it is shaped funny, like the lines don't all match up. So it moves forward and it moves back. And so this forward goes into low pitch. So at low pitch, the decreasing forces are greatest, meaning the aerodynamic is more than the centrifugal, and the blades move forward to pitch to permit the engine to develop full takeoff power. During climb, maximum power is made available due to the fact that the blade pitch increases as the velocity of the airplane increases. So remember too that this is going to come into effect, this factor with this triangle that we looked at before. I told you it's complicated. The triangle we looked at before, and if we tie that into this, let me see, pen, tie that into this, we have this triangle where this is RPM, this one right here, but this is aircraft speed. So aircraft speed. And the more the aircraft speeds up, the more it's going to change this hypotenuse, which changed the angle right here. And so with that angle change, as the aircraft speeds up, so the air hits it a little bit differently and then starts driving it back towards this high pitch angle. So what else do I got here? By maintaining a given cruise RPM, constant horsepower of the engine is available to altitude up to critical, cruise critical. I guess it's not important. Let me see. It uses natural forces acting on blade and counterweight to achieve proper blade angle. I already said that. I think that kind of sums it up. I mean, I could keep showing you. What do I have here? The center line of the propeller is behind the center line of the hub. I didn't mention that, but that comes into play and why this funky angle that it has. And I think that's this one. The center line of the propeller is behind the center line of the hub. This angle remains constant throughout blade movement. The blade moves forward of hub plane of rotation at low angles, and I think it's this one says it better, and backwards at higher angles. So anyway, I'm not going to keep going with this because I think it just gets even more and more complicated. But just to know that, I mean, whoever thought of this, it's like, wow. By the way, this right here, where are my pins upside down and backwards? This right here, this is my counterweight right here. So, so that's what's happening to this thing. So you're using centrifugal twisting force on the counterweight out there. We're using aerodynamic forces and the angle at which the relative wind is hitting the blade to drive it back. And so it gets kind of weird. So I don't know, maybe I just confused you and hurt you, but I told you if you didn't understand that, it's okay. Just I wanted you to understand all of this difference.
So the counterweight has to be really specific, huh?
Very specific.
That's all the job, basically.
Yes.
That's pretty impressive.
Oh. All right. I'll move on from that. Let's see, propeller operation, cruise. I did say this, so propeller operation. Consider a prop and cruise flight. When the throttle is pushed forward, engine RPM and power increase. An increase in RPM increases the centrifugal twisting moment, which tends to decrease blade angle. Wait a minute. Yes, of the blade. No, I'm not going to go through all this. It will just be like overwhelming. So, construction. Let me see. We'll do construction. Construction. The blades are wood. So it's nice and light. The hub is metal, as are almost all hubs, and all hubs are. I've never seen a wood hub. So hub is metal. I think, not sure if it's steel or aluminum. I think it's aluminum. There is a synchronizer. There is a synchronizer. A synchronizer in the hub. That ensures the blades move together. That ensures the blades move together. And we're going to see that with every single type of propeller that, I got all kinds of stuff open. Oh, I want this one. We're going to see that with pretty much every single type of blade that is movable in flight, that it's going to have some sort of synchronizer gear so that when the blade over here on the right moves, it meshes these teeth and meshes those, and it forces the one on the other side to move equal. Otherwise, you'd have two blades to do different things, and that would be a disaster. Let's see.
Man, that would be sweet on the 140.
I know. And I don't know, I've got, boy, my notes. I thought we had a, man, it's like, gosh, a lot of notes. Nope, I just have 2 pages of everything. There we go, back to 1 page. Okay. Let's see. I had stuff like maintenance, same for any other props. Blades should turn by hand. Uneven movement can be a bad bearing or synchronizer. Lubrication. Hub contains an oil supply that must be checked every 100 hours. High oil level causes sluggish or erratic operation, and check for leaky seals at the hub. So I will say this, always check hubs for leaks. Leaks out of any kind of hub is a significant problem. And we're going to talk more and more about that, but that is the same with all blades that have anything. All right, so that was the automatic. So we did ground adjustable. I did an automatic kind of quickly, and I'll do, now this is controllable. Controllable pitch props. And this was more or less I think the line they took of development. So controllable pitch props allow the pilot to select a blade angle, within the propeller design. Sorry, I'm just sneezing. Blade angle within the prop design. So now we remember the automatic. I mean, it was automatic. The pilot had no control, just did what it did. But now we're getting into the controllable, and we can say the controllable may be 2 position or multiple, or you can almost say infinitely variable. Multiple angles. So the first one I'll talk about is the beach Roby. It's B-E, looks like a bunch of B-E-E-C-H, beach Roby. Beach Roby prop. Let me bring it over. And I know I showed you a picture the other day. So we look at it, and we have an electric motor back. Sorry, I don't know what I hit there. Electric motor back here that drives this little gear, which drives the big gear, which then changes the pitch angle. So, a couple things we can look at, and we should be able to discern right away. Number one, based upon this hub design with this big nut on the front, this is going to be
ground adjustable.
Not ground adjustable. This is. Remember, I said this is a controllable pitch, not a taper, but
spline.
Spline. There we go. Reason why it's not tapered is just because I know what airplane this went on. It came originally on the E-185s, which came out with spline shafts. So this was, I believe, it was first used on the Bonanzas. I'm not totally certain on that, but I'm pretty sure it was the Bonanza E225s, I think, or E185s. So it's got counterweights. Counterweights are going to drive the prop to which position?
Low pitch.
Towards feather, high pitch. Because remember, without them, the blades will automatically go to low pitch. So this means that the blades go, centrifugal force wants to take this weight and bring it right up into here. And because of centrifugal force, it's going to want to go in line with the direction of rotation. So because of that, this counterweight, and there's the other one hidden down there, this counterweight under normal operating conditions, when the prop starts spinning, its natural tendency is it wants to come and be right here in line with this split. And since it's attached to this blade, that's going to drive the blade to a feather angle. Now this is a non-feathering prop, so it won't. It's just going to move, from here to here. It has a small arc, but they're using this to drive it that way. Honestly, I don't know why they decided on this one to do that. It doesn't make a lot of sense to me, but they didn't ask me and I don't care. So, okay. So, the fancy airplanes had electric motor. The not so fancy ones just had a little crank inside the cockpit. You would crank it and have this cable that would snake all the way forward to this little pinion right here, and it would just move the pinion, which would then move this gear. Now, obviously, this cannot be spinning around when the prop's moving. This part stays stationary and is mounted to the crank case, while this is all spinning. So we have to look at how that works. So there we have our little pinion gear, and we move this. Remember, this stays stationary. It doesn't spin with the prop. It just moves as the pilot would control it. Then here's a bearing. So you can see the inner race and the outer race. So this outer race has little lugs that would go in these slots. And then this arm is spinning around at the speed of the propeller is. So it's spinning with the propeller. And this arm has a hole somewhere that goes into this actuator pin. So the blade's spinning, this arm is spinning, the inner race is spinning, but the outside here is not spinning. All it's allowed to do is ride inside of here. So when you spin it, it can ride forward and it can ride back, forward and back. So as it goes forward and back, this actuator pin is not at the center. It's actually, it has to be off center, eccentric. So as it moves, it will rotate. Let me see. I think a better way would be to, if you looked at the blade butt, you had something like that. And so it would rotate it this way and then that way, which would rotate the whole blade. Stephen?
So I noticed where it says actuator pin and then actuator, which is really just the bearing. So the pin sit where that lug is, or does it sit in the circle right there into the bearing?
This lug goes into here.
Okay.
This actuator pin goes into a hole in the arm.
Okay.
Or is attached to the arm somehow.
How do you get them in there?
I don't know. We don't do that. Somebody else puts it together. Well, actually, it's not hard because I'll go back 2 slides. Remember, the whole thing is split. You just unbolt it, unbolt it, unbolt it, and the whole thing splits in half. You just lay it together.
The bearing with the lugs in it.
Oh, I don't know. Never really thought about it. How they get them in there. Might put them in there and just press the pin in from, once it's in, press the pin in. So put the bearing inside there without the lug, then press the lug in through the opening.
Was it easy to rotate or?
I've never worked on this one. I've never really done much experience with this one, but if I did, I'm going to tell you that it's probably locked into this, and it's going to be difficult to rotate right and left. I'm not going to want to because it's going to put stresses on here that I don't want. On an inspection for this, what I'm going to do is I'm going to grab the blades and try and rotate them just a little bit to make sure that that it isn't moving too much. And then I'm going to, with any prop like this that has a hub design, I'm going to go out to the tips and I'm going to lift it up and down and fore and aft. I'm going to make sure that everything works, that there's not a lot of slop in there. So I don't, this one's kind of hard to make heads or tails of, honestly. Let me see. The manual drive one, which is actually at the cockpit, rotates a large gear too inside. This gear, a bearing assembly 3, which is just, they have the whole bearing assembly, it's just some red thing there, which I showed you. Here is that actuator arm right there. So it moves the fingers 4, here's the finger, and moves the fingers 4 and aft, which in turn rotates each prop blade. So prop blade here, so 5 is attached to the whole prop blade. And so it comes down and it sits in that little arm. So this drawing is quite different than the one we just looked at, which is why it doesn't quite line up how it attaches, but you can sort of see it here. There's a bunch missing off of this blade. I think they have it all on this blade here, so we can make heads or tails of it there.
So as you crank that gear, whichever way, it makes that arm go back and forth, and that's what rotates the blade.
4 go right here down. We'll look at the bottom. 4 goes back and forth, and as it goes forward, it's got to rotate the prop around, giving you the different pitch. All right, so beach Roby. Beach, let's see, similar to Aromatic, with wood blades and metal hub, with wood blades and a metal hub. Let's see. Oops. That should have said construction, and I got that, so I'm all off. So A is actually construction. Construction, and that would be I, and this would be I. Sorry about that. Bearings. Bearings in the hub allow blades to rotate. Bearings in the hub allow blade to rotate. Now keep in mind, I didn't show you, or we didn't even talk about the bearing. You do have to have blade bearings where they rotate and for ease of rotation. And those bearings take a tremendous load. You think about it, those are the ones really where the centrifugal twist, not twist force, but the centrifugal force is bearing down upon those things. It's bearing down upon the bearings. That's why it's called that. Uses an external gear assembly for pitch control. Assembly for pitch control. And I need to move over, I'm out of space. So you'll tell me when I'm good to move over. Good, all right.
Could you go back just first?
Maybe mechanically driven. This little gear that is driven through the use of a cockpit crank. Use of a cockpit crank that drives a flexible cable, that drives a flexible cable, like a tachometer cable or a speedometer cable, or it may be driven electrically or by an electric motor. With a cockpit mounted switch, with a cockpit mounted switch. If you have the mechanical one, there's got to be some means to stop it. I don't know, they would use some sort of limit in there. If it's electrically, you still have to have some sort of limit. So it would use micro switches. along with mechanical stops to limit travel. Can't have it going too much. One of the things about any sort of prop that changes pitch, if you put too much pitch into it, you slow the engine way down. And then when you slow it down to a point where the manifold pressure gets too high, and it's basically like trying to take off in your car in like 5th gear. It's really bad for it. You get detonation and pinging and all kinds of bad stuff. So operation, which is what we really talked about already. I'm just going to give you some notes here to write if you so desire. When the pinion gear is turned, when the pinion gear is turned by pilot input, it rotates the drive gear. And that's that big gear that we saw. So you have the little gear, which is the pinion gear, and then drive gear, which is the bigger one. And so the drive gear is mounted to the crankcase. Drive gear is mounted, or the assembly is mounted to the crankcase. And let me see, and does not spin with the prop. But the big gear is allowed to rotate, so. Hopefully that made sense, since it says it doesn't spin, but it does rotate. The actuator, I'm gonna go back here. So this big gear is not actually attached to the crankcase because it has to be able to spin right and left, but the assembly that holds it is. And so what I was saying is this gear doesn't spin around at the speed of the engine or the prop. That would be ridiculous. You have the pinion gear and then go crazy, and then you have a little have a handle inside the cockpit that would go nutso. So this is allowed to spin or rotate, but does not spin with the prop. Then we're talking about the lug. So the actuator is a ball bearing with an inner and outer race. So you can kind of see here's the outer race, and then laser pointer. So the outer race, then this part right here represents all the little balls in there where they have just the dashed lines, and you have the inner race. So the actuator is a ball bearing, with an inner and outer race, with an inner and outer race. The outer race has lugs that mesh into the drive gear. Outer race has lugs that mesh into the drive gear. We'll say drive gear slots. That makes sense. So that one's just moving in and out of the slots really and doesn't spin. But the inner race, this is the one going to town. The inner race rotates with the prop. So this one's going engine RPM and has arms. The arms are connected to the blades through the actuator pin. The arms are connected to the blade. connected to the blade. Let me see, 3 actuator pins.
With all that rotating on the ball bearings, how do they get lubricated?
I believe it's grease. All right, see a little grease fitting right there? So yeah, that's called a Zerk fitting, Z-E-R-K, Zerk fitting. And I'm willing to bet there's also one on the other side too. Wherever you see one Zerk fitting on a prop, you usually see another one if you saw it. Now, we're going to talk about grease fittings probably a lot, and I'll remind you. One of the things that gets mechanics into a lot of trouble, these grease fittings, we see them on cars and things, and we think, oh, it's okay just to come up and give it a bunch of grease and, let's grease it until grease comes out of the blade here. Well, that's really, really bad. That usually means you blew out a seal. I'll tell you now, and then I'll tell you again later that most modern new props, you're only allowed to put, I think it's 4 ounces of grease in per year, and they have a maximum amount of X number of ounces of grease that they can hold. And when you reach that limit, you have to have the prop overhauled or disassembled, cleaned, and resealed. And so what happens, a lot of mechanics don't know better, and they just grease the hell out of it and go, hey, well, I've put in a whole tube here and it's still, I don't know, nothing's coming out. And that's okay, because all you have to do is take the prop off and have it overhauled at that point and hope that everything's okay and you didn't just spend 20 grand on greasing. So you have to be really careful and follow the directions exactly. In fact, when it comes to props, they can be so complicated, and the way things are done, I prefer to have a prop shop. I don't shop around. It's like I had a relationship with one prop shop, and that was my go-to shop, and my props went to them. And then if we would come back and, and if I didn't know any better that next year, I'd say, okay, hey, we had the prop overhauled last year. It's in for an annual, remind me again, what grease am I using exactly? Because you can't mix greases, and how much do I put in? And, they would tell you, and that way you're always getting the same information and the same story. It's not like if one prop shop did, something by one service bolt and something did it by a book or a different book, and it didn't match, then you're going to create a mess. That's why you always had like one go-to thing. Just like I said, I would never, when I had tappet bodies and camshafts overhauled and reconditioned, I always sent the cam and the tappets to the same company. I never ever mixed and matched, because then when you had a cam or a tappet that went bad prematurely, you call the people that did the camshaft and go, well, that wasn't us, that was on the tappet people. You call the tap people, well, that wasn't us, that was on the camshaft people. And nobody ever takes responsibility. But if the same person did everything, then there's responsibility there to say, hey, the camshaft went bad. Well, who did the lifters? You did. Oh, we'll send them back. Let's see what happened here. Let's just take care of the situation. So I think it's in the same way I deal with prop companies, and we develop a relationship and trust them, and it's kind of a two-way street. All right. Let's see. When the pinion is moved, did I do this? Let's see. When the pinion is moved, that's the little gear. It rotates the drive gear. Rotates the drive gear. That's the big gear. The drive gear slots. Move the actuator bearing. Move that actuator bearing forward and aft, depending on what you asked for. And then last thing here, when the actuator moves forward and aft, fore and aft, the blade angle changes. And I know you're still writing, so I'll just do this real quick. But I noticed when I was talking to you a minute ago, you can see the mechanical stop right there. That's going to come forward and hit this. So all you have to do is unbolt that. It's probably clamped on there, and you can rotate that a little bit this way or a little bit that way. And that's going to be one of the stops that's going to stop it from going too far.
You also run out of gears on the ring gear there.
I don't think that it did run out of, oh yeah, I guess it does. I can see on the other side of the stop that, yep, it does run out of, but you don't want it to run out of gears. That's for sure. You want to hit the stop first.
You'll just eat up the teeth on the pinion gear.
I know. That's how you limit it. You just grind away the teeth. So how would I maintenance this prop? Well, I talked to you about the inspections, you know, make sure that the blades are in there tight and everything is free and there's no binding up. But other than that, it's pretty much the same as any other prop, same as any other prop. You're going to check the blades for cracks, nicks, tracking, which you know what that is now, loose bolts, safety wire, excessive blade movement. I talked about that, going out to the tip of the blades and trying to move it fore and aft and up and down. At some point, I'll show you actually a pretty good video done by Hartzell, I think it is, that shows how to do that. And on this one, I would definitely lubricate the control cable. Obviously, this one takes grease. I told you that. So you're going to grease per the, all right, I didn't have it before, grease per manufacturer. I'm going to abbreviate that, MFR, manufacturer. Don't over grease. Boy, if you don't know, don't do anything. Call somebody, find out. All right, you caught up there? Steven's still writing. Keep writing, Steven. You're good. Oh, he's got his hand up. We got your hand up for Steven.
Oh, I didn't even know I did. I just finished writing though.
Oh, you good? Okay.
Yep.
All right. Well, it's getting near 7:50, so I don't want to have to force you to write a whole bunch, but how about write anything? So what we're going to talk about next, and I'll talk about it now. We can write about it tomorrow, not tomorrow, Monday. Woo! So before I forget, don't forget, before I forget to tell you, you do have the instructor test is due Monday, so don't forget about that. The next thing we're going to talk about is the Hamilton Standard 2-position prop. And this starts us getting into the world of constant speeds, because from here on out, everything works sort of on the same basic principle. You know, we talked about the ground adjustable. Well, that's just, you know, practically a fixed pitch prop that you can just move on the ground. Then we have the Aromatic, which is its own different animal that works all on its own out there with just a little bit of engine oil for lubrication inside of the hub. No pressures, no controls, no nothing. And then we talked about the Beach, which has got grease certs, and so that's just grease inside there. There's no engine oil, and it's moved off of either a crank inside the cockpit by a cable or just a little electric motor. But from here on out, everything is going to use engine oil. It's hydraulically operated and uses engine oil to do that hydraulic operation. So the things that you have to remember about props is, if you remember a couple of things about how they operate, and you just keep those things in mind, you're going to be absolutely fine. And everything works the same pretty much. Sometimes you have pressure to decrease. Sometimes you have pressure to increase. Sometimes centrifugal force goes one way. Sometimes it goes the other. but all you have to do is look for tattletale signs and application. So application will play a big part in it for the most part when we get into the regular constant speeds. But just to look at this prop right here, there's some things that you should key up on. One thing at least you should key up on right away. And first of all, be thankful that I'm not explaining how this thing attaches, because it's got an inner thing and an outer thing and all kinds of weirdness to get one of these on, and special tools and cones and all kinds of stuff. But it has counterweights. So counterweights tell me something. Now this counterweight is attached to the blade. It's the only reason why you put it there. Without the counterweights, as this prop is operating and under normal operating conditions, there's aerodynamic twisting force and centrifugal twisting force. And the aerodynamic twisting force is going to want to make it go towards feather, and the centrifugal twisting force will always make it go towards the low pitch or low blade angle. But counterweights have been added. So when counterweights have been added, you have to know always, all the time, zero exception that I can think of, a centrifugal twisting force will make the blade go to goes to the high angle almost always. Well, boy, I said that. Now I should tell you, be careful, because sometimes they will use it to help out. So, ooh, I gotta be careful with that. So, just keep in mind that I probably just screwed you up here. This prop's a little bit of an exception, I think. So anyway, these counterweights, which way do they want to go? They want to come down this way, which it looks like it's going to drive that thing to a low blade angle to help it out. But we're going to see what's going on here. But remember, we have counterweights, got to follow those. And let's jump into this one here. So this is my Hamilton Standard 2-speed. All right, and so this drawing, and I know this drawing is going to be jacked up, and it's going to take me a minute to remember and correct it, because yeah, it's just, there's something about it that's wrong. It'll come to me in a few minutes. So what this is going to do is it's simply going to use oil pressure to do one thing and centrifugal twisting force to do another. And that is not going to change on any prop. Oil pressure does one thing, centrifugal does another. So we can look at it right here. It's oil pressure released and the centrifugal form of the counterweights increases blade. Okay, so let me see my pen. Counterweights increase propeller blade angle. All right, so does that hold true with what I said about counterweights always do?
Yeah.
Okay, so good. I did say that right. I'm gonna go back a page. It just looks a little weird because, oh, I know why. Geez, because my head was up and locked. Which way do these counterweights want to go during operation? Do they want to come down here or go towards the center line?
Center line.
There you go. So counterweights under normal operation, centrifugal twisting force is always going to make them go that way. Always, all the time. I'm sure of that, 100% positive. So that means that counterweights always twist the blade, and it's attached to the blade. So that makes that blade want to go
Feather.
Feather. Thank you. So feather. All right. So in this one, oil pressure is being released, and it's just kind of in a weird spot. So these arrows are pointing towards no oil pressure. So without oil pressure, if I take oil pressure out, and oil pressure comes in this dome right here and fills it up and pushes on this piston, and the piston goes forward, and and I'll show you that in just a second. So what this one is doing is it is currently going towards, has been released, and the centrifugal force is increasing the blade angle. So that's what they're showing here. Currently, the blade angle is being increased because there is no oil. So no oil or oil released equals high blade angle. All right. And this one, oil pressure is added. So I think why I hate this one so much is because the piston is all the way back and they're saying oil, but it's about to be filled full of oil. Hasn't been filled full of oil yet. That's why it is. I hate it. This one has been filled full of oil, And it is now in, it is, so, oh geez. It is in this position and it's going to go this one. So it is a low blade angle. See how this can get a little difficult. You got to keep me honest because I'll screw up sometimes. So it is currently in the low blade angle, but as oil is released, when it is released, it's going to go towards a high blade angle. So it's going to move that way. That's why I hate this drawing. All right. So this one, it is currently in the high blade angle. And by adding oil pressure, it is going to move towards the low. So the counterweights have, geez,
I think the writing is backwards.
Is that what? Yeah. Something's wrong with them.
Yeah. If you use this for the other one, makes sense, you know?
Yeah, that's, I think what I've done every year is like, I should just cut and paste it and make my own drawings. So oil pressure is released, centrifugal force on the counterweights. So, all right. And maybe I'll look at that over the next day or two and figure out if that would make more sense and rewrite my own slides.
This should be 85 and then the other one 86.
Yeah. And you know what? Every book does this. So once one person made, and I've looked through all of them, they all say the same thing. But okay, but I'm sure of this. When the oil fills this up and it pushes this way, so ignore the arrows, oil is going to push it this way. And as it pushes this way, it's going to act on these counterweights and it's going to slide out and bring it into the position that it's in right now. So oil pressure brings it into this away from feather. So oil pressure, oil to low angle.
So they're basically acting opposite of each other.
Always. Oil pressure will always act the opposite of the counterweights.
So since it's taking it further away from feather, if you lose oil pressure, I mean, typically you have to feather yourself, but shouldn't it? If it's bringing it away.
Okay. So you're getting ahead of yourself. This is a non-feathering propeller.
Okay.
It moves about that far. That is, it has a very, very low amount of movement. That's it. You're looking at it. It's just a few degrees. And that makes a big difference. Remember, 1 degree is like 60 to 90 RPM. So 2 is up to 180 RPM. So it's really low. So, so oil goes to low angle and centrifugal twisting force to high angle. And that's not a hard thing to remember, right? So, and it coincides with that. Oil pressure released, centrifugal twisting force on the counterweights increases blade angle. So centrifugal twisting force to high angle. And I told you that a bit ago, whenever you see counterweights force the blade to a high blade angle. So every time you see counterweights, see counterweight, then oil to low pitch and centrifugal twisting force to high pitch. Always. See counterweights, then oil to low pitch. So you lose your oil pressure, this counterweight's going that way, and this blade's going to high pitch. Add engine oil, it's going to act on the piston. It's going to override the counterweight. These counterweights, they're actually they're hollow, and there's really not much in them, believe it or not. There's some stop pins in them. Lose oil pressure, or add oil pressure. The oil pressure is going to counteract that. It's going to drive this counterweight back down and bring this to low pitch.
So we increase oil pressure when we take off, and during the cruise we decrease oil pressure, right?
Yes, sort of. And I think it's time to go. I don't have my clock up here. Hang on. So let me see. Oh, I got a minute. So I'll just throw this out at you. There we go. So in this particular one, there's no governor or anything. You just have a 3-position valve. You either have oil or you don't have oil. So you have engine oil pressure comes in here. You either port it over here to the propeller, or you rotate it and it's going this way. Maybe I have another slide on it. And it's going that way and it's draining it. I don't know, maybe I do have the next one. No, I don't. Okay, so either that or you're draining it. So it goes from the propeller and just drains back into the crankcase. So yes, oil, no oil. It's, what do you call that? What's the word I'm looking for?
It kind of fits with the 2-position prop. It's like a 2-position switch.
It is. Oil pressure, yes. Oil pressure, no. Binary, that's what I was thinking. I knew it was a B word. So it's a binary operation. You either have oil or you don't have oil. And I'll cover this again on Monday. So I'll start here. We'll go back through it. Maybe I'll take those slides and reword them and make my own so that it's not confusing. They go, oh, I get it. Because yes, they are backwards. But anyway, so well, have a good weekend, everybody.
Yep. Thanks for the knowledge.
Thanks for all the knowledge, Kevin.
Hey,
Hey, you're welcome.
Thanks,
thanks for the
Thanks for the
knowledge,
knowledge.
Kevin.
Thank you.
Don't be a copycat, Zach.